Chapter 12, the basics of solving equations. And we start out with something that you're going to probably spend most of your time combining like terms when you're trying to solve an equation. So we have a list of terms on the left and then a different set of terms on the right. And we want to match the terms on the left to the like terms on the right. So if we read our workbook, it simply states that two terms are like if they have the same variables and the same exponents. The same variables. Alright, and so we not only see variables and exponents down here with these terms, but we see what we call coefficients. So I'm going to go through here and point out or circle the coefficients. 2 is a coefficient. 8 is a coefficient. This term z squared also has a coefficient. It's not written, but it would be understood as 1. 7 is a coefficient. 4, 9, 5, and all of these numbers are on the level with the variables, and they're sitting in front of the variables. They're not a subscript or superscript like an exponent is. So these are the coefficients. Like terms do not depend on the coefficients. So we don't even consider these numbers that I just circled. So let's match the like terms. Alright, on the left column, and we're matching left with right. First term that we run into is 2x squared y. And we look down the list on the right, and here we have a 5x squared y. Okay, they both have an x. The x is also squared in both cases, and then they both have the y variable, and we could say that that exponent of the y variable is 1. So now we just simply draw an arrow from 2x squared y because they're like terms. Also, notice that we call all of these terms in that we only have multiplication, and some variables have exponents. There is no addition or subtraction involved among the numbers and the variables. So what about 8mp? We're looking for an m and a p, and we want the exponents to be 1 for each variable. We look at our column on the right, and here is an mp term. Okay, the one above it is n, and so 8np is not like 8mp. So we only draw an arrow from 8mp to the 3mp. Different coefficients, but same variables with the same exponents. Z squared matches the 5z squared. Xy squared, and here we have an xy squared on the bottom of the second column. Now keep in mind, directly above the 9xy squared we had a 5x squared y. Same variables, but we didn't match the 7xy squared to that term because the exponents are different. With the 7xy squared, x has an exponent of 1, and for this term the x has an exponent of 2. The exponents don't match. And finally, the last term on the left, the mp term, matches with the 8np on the second column. So here's a definition: coefficient. It's the numerical factor. And so if you look at each of these terms, like I stated before, everything involved with the term is being multiplied, such as this 4np. The 4 is multiplied times the n and multiplied times the p. So we have a factor of 4 in this product, we have a factor of n, and we have a factor of p. So if no numerical factor appears, the numerical factor is considered to be 1. And as I pointed out with the z squared term, we could interpret that as a 1z squared. Moving along, the last paragraph of the page reads that any like terms may be combined using the distributive property. So here we have a 3x plus a 5x, and notice that we have a term, an x term, plus another like term. This plus symbol in between represents addition, so we're adding two like terms. So what we can do is just simply take the coefficients, add them together as we usually would, and get an 8. 3 plus 5 is 8. And then put the common variable part behind the 8. So an x, 3x plus 5x equals an 8x. Notice that we didn't put an x squared. We simply added the coefficients, nothing else. And we can only do that when they are like terms. So that takes us to example 1. So with the first page of this chapter out of the way, we can work these examples in example 1. And so by combining, we're simply adding or subtracting various terms. And if they are not like, then we simply cannot add or subtract them. And so we compare these two terms, 3m and 4m. Do they have the same variables, and do they have the same exponents? Well, obviously they both have an m. Neither one of them have any other variables, and the exponent of the m in both cases is 1. So what we can do is just add the coefficients and place the common variable part behind that sum. 3 plus 4 is 7, and so we would write 3m plus 4m equals 7m. We did not fool with the exponents. The exponents stay the same when combining like terms. Here we have two terms that are like, and they are subtracted. So we sort of ignore the variables and we say 8 minus 6. We focus on the coefficients to actually carry out the subtraction. What did they have in common? Well, they had a z. Subtract 6 from 8, we get 2, and we place the z behind that. Next example, we can interpret this as a 3q plus a 1q when a variable or a set of variables that are multiplied together do not have a coefficient listed. We interpret that as a coefficient of 1. So both of these terms have a q, and both q's have exponents of 1. And so we say 3 plus 1. We attach a q to that. In the end, we get 4q. Example 1d, we look through our list of variables. Here we have, or terms, we have 6r minus 8s plus 2r minus 3s. So we're adding and subtracting several terms. What we have is 6r. We can only combine that with one of the other like terms. The only other term that is like 6r is 2r. In the previous chapter, we said that if we are adding or subtracting, well, not subtracting, I'm going to rewrite this in terms of addition so that you don't get confused. But whenever we're adding multiple things, numbers or variables, we can change the order that we add those things in. In this case, we call our things terms. So I'm going to rewrite this as a plus a negative 8s plus 2r plus a negative 3s. So in other words, you simply have to realize that the operation in front of the term simply follows the coefficient and the variables. So in this case, we take our like terms, 6r, and then we have a plus 2r, and we combine those two terms. Because the other two terms have an s. They don't have an r at all. So we can combine these two by saying 6 plus 2 and placing an r behind that sum. Then we can say plus, and our remaining two terms are alike. They both have an s term, and their exponents are the same. And so we say negative 8 plus a negative 3, and we put an s behind it. We perform the addition, and we get 8r plus a negative 11s. And in the end, you could write this as 8r minus 11s. Or depending on the number or the order that you rearrange the terms in the beginning, you can say minus 11s plus an 8r. So to work the next example, E, I'm going to erase some of this. E, similar situation to D. Here we see that 6CD in this expression only has one other like term, minus 7CD, and then the remaining two terms, plus 5C and minus C, are like as well. So if I wanted to, I could place the like terms side by side by writing 6CD minus 7CD. Notice that the subtraction symbol went along with the 7, and then behind it I could place 5C and then subtract C, so that now my like terms are side by side. With the first pair of terms, I could write 6 minus a 7 CD, and then I could write plus, and the second pair of terms, 5C and minus C, I could write 5 minus 1 with a C behind it. So this first set of parentheses would give me a negative 1, and then I simply tag a CD behind the number. The second set would give me a plus 4 with a C attached, and then if you want to drop the 1, that's fine, just don't drop the sign. In the end, you could write this as a minus CD plus 4C. Likewise, you could write this as a 4C minus a CD. Our last two parts of example 1, we have sets of parentheses from the beginning. So from the previous chapter, we will have to apply the distributive property. With the first set of parentheses, we're taking the sum t plus 3u and multiplying both terms by negative 5. So, negative 5 times t would result in a negative 5t. Then a negative 5 times a plus 3 is a minus 15, and we would place the u behind the negative 15. So negative 5 times a plus 3u is negative 15u. And now that we've distributed, we no longer need parentheses. We move on to the addition in between. We distribute the 2, and so we say plus 2 times a 7 would be a positive 14, and we attach the u behind the 14. Then we have 2 times 4t, which would result in 8t. 2 times 4 is 8, and then the 4t term had a t, so we place a t behind the 8. We can rearrange our terms. We have a minus 5t. What other term in this string of terms is like the minus 5t? That would be the plus 8t on the end. So we'll put these side by side. We'll write those as our first and second term. 8t had a plus in front of it, so I'll write plus 8t, and then I'll just write out the other two terms, minus 15u plus 14u. And so we can only combine the t terms, which would give us a negative 5 plus 8 with a t attached. And then we can combine our u terms. So the best we can do is simplify this to an expression that has two terms in the end. So we could write plus parentheses with a negative 15 and a plus 14 inside, and then put the u behind the parentheses. For the first set, we have negative 5 plus 8, which is 3. So we write 3t. We have addition in between. In parentheses, we have a negative 15 and a plus 14. That would result in a negative 1. And then we attach the u to that coefficient. And this is the best we can do. In that we have two terms. We can't combine these two. This is a t term, that's a u term, different variables. We could write 3t, and then we could drop the 1. We could also say that plus a negative is the equivalent of subtracting. And so if you wanted to, you could write this expression as 3t minus u. Or you could reverse the order of the terms and write minus u plus 3t. With g, we have slightly different situation, only one set of parentheses. And now the number that we distribute across that set of parentheses is behind the parentheses. So in this case, we would take 2 and multiply the 3x, and then take 2 and multiply the 5z. Alright. And then we just simply write out to the side the remaining terms. So we would say 2 times 3x. It doesn't matter whether you put the 2 in the front or behind the 3x. The addition sign in between the 2. Then we distribute the 2 to the second term in parentheses, so 2 times 5z. And then we just simply write out to the side the remaining terms. In the next line, we could carry out the multiplication of the coefficients. 2 times 3 would be 6, so we'd have a 6x. 2 times 5 would be 10, so we'd have a 10z. And then again, just simply rewrite the last two terms. Rearranging the terms to where the like terms are side by side, I could write 6x minus 8x. That takes care of those x terms. And then all I have left is a plus 10z plus 3z. And so with the expression the way it's written here, I can only combine the first two terms and then the third and the fourth terms. 6 minus 8 is a negative 2. Oh, and I wrote a z. I'm supposed to write an x behind that. So 6 minus 8, negative 2, and we have, we combined x terms. So we write x behind the negative 2. Then we have a 10z plus a 3z. 10 plus 3 is 13. And we combine z terms, and so we simply write a z beside the 13. And we end up with two terms, and this is as far as we can go. We cannot combine this x term with the z term. We could write them in a different order, but that's all. In the end, you should end up with either of these two expressions, negative 2x plus 13z, or a 13z minus 2x. So that completes example 1, and we will move on to the next page. Oh, we had another example. We have h. So let's work this one, and then we'll be finished with example 1. Here we have some exponents, and so there is an x squared term, and so here we have another x squared term. Notice that these two terms, the 3x squared and the minus 9x squared, are not like the 4x. Yeah, they all have an x, but these first two x terms have x squared. So this exponent for the 4x is different from these two terms. And so other common or like terms are the negative 6 and the plus 14. I just place a star above those. And then plus 4x is the only term of its kind. So I'll just put a box around it. So in the end, we cannot combine the 4x with any other terms in this expression. So we'll combine the x squared terms first, and that's going to look something like this. Parentheses with the x squared. We're simply going to add or combine the coefficients in the parentheses. Then we're going to have an x term, and then we're going to have the constants, just the numbers with no variables. So with these sets of parentheses, I can simply run through here. For x squared, we have a negative 3 minus 9. For the x term, we only had a 4, so there's no operation to do inside this second set of parentheses. And now for the constants, the numbers with no variables, we have a negative 6 plus a 14. So we've used the 3, x squared, the minus 9, the 4, and then in the last set of parentheses, the negative 6 and the 14. So we've used up all of our terms. Running through this expression one more time to just simply get rid of the parentheses, we have 3 minus 9 is a negative 6. We can drop the parentheses for the 4. There's no operation inside. Inside this last set of parentheses, we have a negative 6 plus a 14, which results in a positive 8, and so I'll just write an 8. And so with this expression h, example h, we can only narrow this down to 3 different terms. We can't simplify this expression any further. None of these 3 terms are like. So now we're going to talk about equations, and this is what we're going to spend the majority of our time on in intro algebra and a large part of intermediate algebra for that matter. Solving equations. Okay. And most of the equations in intro, the majority, will involve only one variable. Okay. And as before, we mentioned that a variable just represents an unknown number. And so as we have written near the bottom of the page here, here's an expression, or not an expression, but an equation. And if you look throughout the equation, we have only one variable. We have an x. Okay. So eventually we'll get around to talking about how to find x, but for now we're just concerned with talking about what it means to have a solution to this equation. So a solution would be a particular number that we can take our equation and replace x with, carry out the order of operations, and obtain the same number on the left side of the equation as we get on the right side. So LHS, when you see it in this workbook, stands for left hand side. RHS, right hand side. So we can break up this equation into these expressions: 2x minus 4 on the left, and on the right, x plus 1. And it states that x equals 6, or it's asking if x equals 6 is the solution. So real simple. To figure that out, we simply replace the x with a 6 in each expression on the left and the right. We carry out the order of operations. With the left hand side we have multiplication and subtraction, and so we multiply first, and we get 12 minus 4, and 12 minus 4 results in an 8. Now we check the right hand side and we add 6 and 1, and we get a 7. And so the two sides do not equal. Therefore, we say that x equals 6 is not a solution. X equals 6 is not a solution. And this is one method of solving equations. It's definitely not an efficient one, but we could solve equations with trial and error. We could simply guess as to what number the variable was, plug it into the left and the right side, calculate the two sides, and if they're equal, then hey, we made a good guess and we solved the equation. Next question says, is x equal 5 a solution? So again, we have the same equation, except we plug in a different number. We're going to check 5. Plugging 5 into the left-hand side, we have 2 times 5 minus 4. Order of operations dictates that we multiply the 2 and the 5 first, and then we subtract 4, and we get a 6. Let's see if the right-hand side gives us a 6. X plus 1, replace the x with a 5, and now I have 5 plus 1, and I get a 6. So the two sides are equal. And so we would say x equals 5 is a solution. So if we ever ask you to check your solution, this is what you would do. This is the procedure. Once we get to talking about solving equations and you find your answer, or what you think the variable, what number you think the variable is, take the original equation, replace the variable with your answer, and if it is the answer, then the two sides should equal. If not, then you would know that you perhaps made a mistake. Example 2. Identifying solutions to a linear equation in one variable. Two-step equations. For each value of x, determine whether it is a solution to. Here is our equation. So in relation to the two questions that we answered on the previous page, we have a left-hand side and then we have a right-hand side. And lucky for us, the left-hand side is already worked out, so to speak. We simply have a number. So the only side that we really have to calculate is the right side. So on the right we have a 9, and then in parentheses the 9 is multiplied times x minus 2. Here in the table we are given various values of x. So for each row we have to do a separate calculation. So the first question is x equals negative 10. Is that a solution? We take x equals negative 10 and we plug it into our right hand side expression. That will give us a 9 times 10 minus 2. And since here we have the 10 minus 2, the subtraction contained within parentheses, we do that first. Calculating an 8. And now we multiply by the 9, and we get 72. Okay, so on the right hand side we calculated 72, but now on the left hand side we still have this negative 36, and those are not equal. So we say no, x equals negative 10 is not a solution. Okay. Now we have x equals 3, and so once again on the right hand side we calculate 9 times x minus 2, with x being 3, we would have 3 minus 2 in parentheses. 3 minus 2 equals 1. 1 times 9 gives us 9. And once again, that does not equal negative 36 that we have over here on the left. So 3 is not a solution. Now we're asked to check x equals negative 2. plug that into the right hand side, which is 9 times x minus 2. We would have negative 2 minus 2. Calculating the parentheses first, we have a negative 4, and 9 times 4 is 36, and we count only one negative with this multiplication, and so that would be a negative 36. We arrived at this negative 36 by calculating the right hand side, and negative 36 is the left hand side. So right hand side equals the left hand side when x equals a negative 2. So x equals negative 2 is a solution. So we'll check yes for negative 2. And our last x value, x equal 8. Plugging x equal 8 into our right hand side, we would get 9 times 8 minus 2. 8 minus 2 is 6. 9 times 6 is a 54, but that does not equal the left hand side. So x equals 8 is x equal 8 is not a solution. No. So that completes example 2. And now we get into a talk about our strategy for solving equations without the trial and error method. So on the previous 2 pages, we were simply testing a particular number as to whether it was the solution or not. Now what we want to do is find the number. Okay. So we have this additive property of equality. And it basically states, in regards to an equation, what we do to one side, we have to do to the other. And specifically, we're talking about adding. So here what you see is a 5 equal 5. This is a true equation. We're not necessarily concerned about what number we have here. Just that the two sides are equal. So if we start with the true equation, 5 equals 5, we could have 10 equals 10. And the same would hold true. But in this case, we have 5 equals 5. And what happens if we add a number to just one of the sides? And we have that written out here. We've taken the equation, and below the right hand side we've wrote a plus 2 and nothing below the left hand side. What happens? Well, we get an equation that's no longer true. We have 5 equals 7. Here on the right we have the same situation except in general. It's simply stating that this applies to any number. If we have an equation where a number equals itself, a equals a, and we take only one side, in this case we take the right hand side, and we add another number to it, b. B could be any number. It could be a different number than a. If we add a number only to one side, then we get an equation that in the end is no longer true. A does not equal a plus b if b is not 0. So what we want to do is not maintain the number that we have on both sides. Uh, the specific number is not important. It's just simply we want to maintain the truthfulness of the equation. And in terms of addition, in order to do that, we have to add the same number to both sides. So for instance, in this equation, if we wanted to end up with 7 equals 7 in the end, then we would have had to have written a plus 2 underneath the 5 on the left. So at the bottom of this page, we have an equation with no numbers in it. And so we're simply stating that in general, if we have an equation where x is our variable, this is some number that we don't know, and a and b are actually numbers. So for instance, this particular case, we could have the equation x plus 1 equal 2. There are many different combinations of x plus a equals b. This is just one of them. And so what are we saying in this second part? Well, in general, it says that if we want to figure out what x is, we merely do the opposite of what's happening to the x. So here we're adding a positive a. To get rid of the a, on the left side, all we have to do is add the negative of the number, the opposite. So in a sense, we are adding a to x in the equation that we're given. To get the x by itself, we subtract a. A plus negative a equals 0 on the left. But in order to keep the equation true, we do the same thing to the right, plus a negative a. And so in the end, we have x plus 0 equals b plus a negative a, or written a different way, b minus a. And on the left, you just simply have to realize that x plus 0 can be written as simply an x. So a lot of things can be concluded from this general example. To solve for a variable, you simply have to isolate that variable. So you want to get the x by itself equal some number on the opposite side of the equation. Also, in order to do that, you undo the operations that are happening to the x. So to follow this similar procedure with the example equation that I wrote above, we could write x plus 1 equals 2. What is the opposite of adding a 1? Because that's what's happening to our x on the left. Well, the opposite of adding a 1 is subtracting a 1. According to the top of the page, if I want to keep this equation true, then I have to carry out the same operation for the right-hand side. So now on the left side, a plus 1 minus a 1 gives us x plus 0. Subtracting 1 from the 2 on the right gives me a 1. And then x plus 0 is simply x. And so here's our solution. X equals 1. And we have gotten the x by itself. We solved the equation. If you take x equal 1 and you plug it back into the original equation, x plus 1 equal 2, we would have 1 plus 1 equal 2, and that is true. So, example 3, we have ABC equations, and we're simply going to follow the procedure that we've learned from the previous page, which is to basically undo the operation that is happening to V. So opposite of addition is subtraction. The opposite of subtraction is addition. The two operations undo one another as long as I simply add or subtract the same number, which is sort of a different take on what was shown in the previous page. On the previous page, we showed that we add the opposite of the number. So I'll work this first one both ways. Previous page stated specifically that we are adding a positive 7. So to undo that, we add a negative 7 to both sides. So a plus 7 plus a negative 7, the addition of two opposite numbers. And you need to realize that I'm simply writing what I'm doing to each side underneath the side. So to rewrite this a different way, you could write V plus 7 plus a negative 7 on the left hand side, and then on the right hand side we could write 15 plus a negative 7. We're really just trying to establish some method of bookkeeping. So in either case, on the left, the 7's result in a 0. On the right, we simply carry out the addition and we get an 8. V plus 0 is equal to a V. Okay, and so all I've done is just simply rewrite this as a V. It's still on the left hand side, and in this case nothing changes on the right hand side. We simply have a number, and so here's our solution. V equals 8. If you take 8 and you plug it back into the original equation, V adds 7. Well, V is 8, so 8 adds 7. Do the left-hand side and right-hand side match? Well, yes, they do. 8 plus 7 is 15, and the right-hand side is 15. So this is just simply a way of checking our solution. But our solution is V equals 8. Now, this is sort of the version of the how to solve this equation in terms of adding the opposite of the number. And some would argue that we're sort of splitting hairs here. This basically leads to the same equation, but I view my favorite explanation is simply the opposite operation. And so from my perspective, what are we doing to V? Well, we're adding a 7, and so I do the opposite. I subtract 7 from both sides, and always keep in mind that you want to carry that out on both sides. The 7's cancel. We get a V on the left. I simply do not write out the 0. Yes, 7 minus 7 is 0. I just don't write it out. And then on the right, I have 15 minus 7, and I get an 8. Okay. And so this is how I approach at least these simple equations here. I do the opposite operation. So with b, what is happening to the variable p? Well, if you simply say out loud the left hand side in words, you would say p subtract 3. So we're subtracting 3 from the p. The opposite of subtraction is addition, and so I simply say add 3. But I have to write add 3 on both sides of the equation. On the left hand side, you could see this written as p minus 3 plus 3. The right hand side could be written on the same line, 1 plus 3. Really no need to write it both ways. You simply want to realize that the 3's cancel on the left, leaving you with a p, and then on the right we have 1 plus 3, which is 4. So these are merely simple one-step equations. Okay, we only had to carry out one operation to both sides in order to get to the solution. So p equals 4. If we follow the original equation and we subtract 3 from p, 4 minus 3 equals 1, and 1 is the number that we get on the right hand side. So our solution checks out. For c, we have m plus 12. We focus on the side with the variable. Okay. The question is, what is happening to the variable? Well, the variable m is only on the right hand side. So on the right hand side we have m plus 12. We're adding 12 to m, so we do the opposite and subtract 12. On the right, the 12's cancel. We're left with an m. And then on the left, we calculate our solution, 4 minus 12, and we get negative 8. Which makes sense if you plug it back into the original equation. M plus 12, we're saying that m is negative 8. If we take negative 8 and add 12 to it, what number do we get? We simply get 12 minus 8 is 4, and that equals the left hand side. So our solution checks out. With the example on the bottom of the page, similar one-step equation, except now we have decimal numbers instead of whole numbers. So in words, how would you read this expression out loud? X subtract 3.6. What is the opposite of subtraction? Well, it's addition. So in other words, to solve this equation, we simply want to add the number instead of subtract it on both sides. So what I write is x minus 3.6 equals 7.1. I just simply copy it down. And now underneath, and this dash line is simply just to separate the left hand and the right hand side. Left hand side, right hand side. We're doing the opposite on both sides, so that would be to add 3.6. A negative 3.6 plus a 3.6. The two numbers cancel, leaving a 0. So on the left, all we have is an x, and now on the right hand side if we add 3.6 to 7.1, I would get a 10.7. So x equals 10.7. Same version of the examples above, except we're dealing with decimal numbers. Here we have an example with mixed numbers and fractions. We focus on the variable. The variable is only on the right side. According to the right side, what is happening to y? Y add 1/2. Y plus 1/2. So in order to get the y by itself, we simply subtract off the half. But if we subtract a half from the right, we have to subtract a half on the left as well. So finding our solution only takes one step, but now we are left with subtracting fractions. So actually calculating the solution is a little more involved in that we have to find the common denominator for the fractions. But 6 and 2, lowest common denominator is 6. So nothing changes for the first mixed number. And now 1/2 would simply translate to a 3/6. And again, we're simply working with the left-hand side. 3 and 5/6 minus 3/6 would give us 3. And 2/6, which can be simplified to 2 and 1/3. And so this is what our solution is. Y equals 3 and 1/3. Okay. So here we see addition between the u and the 3/4, but now the number 3/4 is actually sitting to the left of the variable. And so what you need to look at in terms of what's happening to the u is the sign in front of the number. Okay, so different ways you could look at this. My take is this is plus a negative 3/4. So a negative 3/4 is similar to subtraction. If we were to write this in a different order, the sign would have to go with the 3/4. So what I'm saying is simply that you could write this as u minus 3/4 equals 5/8. So the number 3/4 is actually being subtracted from the u. So to solve this equation, I am going to write plus 3/4, since addition is the opposite of this sign in front of the number that I want to get rid of. If I get rid of this 3/4, then I will simply have my u by itself, which in essence is the goal of solving an equation, just to get the variable by itself on one side. So I'm going to add 3/4 to both sides. Plus 3/4 knocks out the minus 3/4. I bring down my u on the next line. It's now on the left side by itself. And on the right, I have 5/8 plus 3/4. And so still only a one-step equation in that I just added 3/4 to both sides, and as if I could just calculate this with my calculator, I'd be finished. But unfortunately I'm adding fractions without a calculator, and so I need to find the common denominator. Smallest number that 4 and 8 will divide into would be 8. So the 5/8 doesn't change. However, the 3/4 would become a 6/8. Okay, 2 times the denominator scales the fraction up to a 8 on the bottom, and so I multiply times 2 on the top as well. So 3 times 2 is 6. and 5 plus 6 is 11, and that would be my solution. U, we basically have a chain of equal signs. U equals, and now we have the number all the way over here on the right. U equals 11 over 8, and if you wanted to rewrite that on a separate line by itself, that would be fine. We could simply at this point write U equals 11 over 8, and this would be our solution. Example 6, additive property of inequality with integers. I'm simply going to write this a little bit bigger. And so the way I interpret these problems is I look at the sign as indication of the operation. And so if I read out what is happening to the u variable, then I would say in words, u subtract 6. And the goal of solving any equation is simply undoing the mathematical operations that are happening to the variable. So if in my equation I'm subtracting 6, to get the u by itself, I would simply do the opposite operation, add 6. So now if I add 6 on both sides, the 6's cancel on the right, only leaving a u. So still just a one-step equation, and adding 6 on the left would give me a negative 3. Example 7, this is an equation with a slightly different occurrence than we've seen in the previous ones. Here, what you need to notice is that we now have a negative sign in front of our f. So one way to fix that without using multiplication or division, which we'll talk about in the next chapter, one way to fix that is to simply say, well, I can take this side with the variable and read it as 7 subtract f. I'm subtracting the f on the right, and so that's what's causing the f to have this minus sign in front of it, because I'm subtracting it. If I want to change the sign, what I could do is I could add the f instead of subtracting it. But the same rule applies to variables as they do for numbers. What I do to one side of an equation, I must do to the other. So now f is a particular number, and so if I subtract a particular number and then add that particular number, these two operations cancel each other. A negative f plus an f is 0. So on the right hand side, I'm now left with the 7 only, and on the left hand side I now have a positive in front of my f. So I can write this as positive f plus 6. I cannot combine the f and the 6 because, as we talked about earlier, these are not like terms. The 6 does not have an f variable. So on the left I now have f plus 6, which is the type of equations that I solved above. So we fixed the problem of the variable having the negative sign in front of it. And now we say, well, what's happening to the variable? We could read this as f add 6. So we're adding 6 to the variable. We want to undo the addition of 6, and so that leads us to subtract. Oh, subtract a 6, not a 7. Okay. So subtract 6. But we don't just do that on the left, we do it on the right. Subtract 6 from both left and right hand side. On the left, the 6's cancel. Plus 6 minus 6 equals 0, and f plus 0 is simply an f. And then 7 minus 6, we get 1. Okay. And as usual, we could check our solution. Simply take the original equation, which had the minus or subtract sign in front of the f. Replace the f with a 1, and we're only replacing the f. We're not replacing the sign. Once we do that, we only have to calculate the right hand side. 7 minus 1 is 6. And so our solution checks out. F equals 1 is the solution. Okay, so that takes us to the next property that we're going to use for solving equations, the multiplicative property of equality. Okay, it simply says or makes a similar argument as we made with addition. If we start with a true equation and we multiply both sides of the equation by the same number, then we get a true equation. Okay, if we only carry out multiplication on one side and not the other, then the equation no longer holds true. Here we have one such equation where a is a number and b is a number, and we want to solve for x. So one such equation, an example of that type would be 2x equals 6. Okay, so I'm sure a lot of you are probably thinking by now, well, in this case, or these types of equations, the answer is pretty obvious. X is a 3 because 3 times 2 is 6. Well, that's true, and I'm glad that you recognize that, but the goal of this chapter is to lay down the procedures for solving equations, and a lot of times there are actually multiple steps to solving an equation and not just one. And so when we get to equations that have multi-step, then you can no longer rely on these simple or I guess your mind just simply giving you the answer. Okay, you're going to have to follow steps, and so we're going to practice these simple ones first to sort of lay down the groundwork for solving the more complicated ones. Okay, and so let's see what they do to equations that fit this format. Well, they use the multiplicative inverse of a number. In this case, a is our number that we want to get rid of. It's sitting in front of the x, and we want the x by itself. So what we do is we multiply by the inverse, 1 over a. Okay, multiplying the left-hand side by 1 over a cancels the a out. And in this case, when I say cancel, we are getting a 1. We're not getting a 0. So we multiply the left by 1 over a, and so according to above, we have to do the same thing on the right hand side, and so we write 1 over a times b. And here we see that 1 over a times a gives us a 1, which is the equivalent of simply having an x by itself. And now on the right hand side, we see that in order to calculate x, we simply divide b by a. Okay, so if you look back at the original equation, you could have simply stated that, well, a is multiplying my x, so I want to carry out the opposite operation, which is to divide by a. So you simply could have written divide by a on both the left and right side, crossed out the two a's. A divided by a is a 1, and then on the right hand side you'd have your solution. If I carried out that same procedure with the equation that I wrote over here to the right, then I would simply say, well, x is being multiplied by 2, so I do the opposite and I divide by 2 on both sides. On the left hand side, the 2's cancel and I get x by itself. Okay, this is left hand side, this is left hand side. And now I simply calculate on the right 6 divided by 2 and I get a 3. And so this is my solution. Okay, so if we simply stick with the argument that we simply want to undo the operations that are happening to the x, then we're safe. If you multiply x to solve the equation, you divide by the number that's multiplying x. Okay, so what's happening here to the t? T is our variable. Well, this is 5 multiply t. Okay, stated another way, this is t multiply by 5. As the previous chapter stated, you can write the multiplication of two numbers or variables in opposite order. So we could say this is a t times a 5 equals 75. Okay, but the point is that what we want to do to solve this equation, or stated a different way, get the t by itself, is we want to take both sides and divide by 5. So I simply take both sides and put a fraction bar underneath, and then I write 5 underneath that. On the left, I showed that the two 5's cancel. 5 divided by 5 gives me a 1, which now sits in front of the t. On the right, 75 divided by 5 is 1. 5, 15. And on the left, well, a 1t is simply a t by itself, which means that I've now solved the equation. And we still consider this to be a one-step equation. We only had to carry out one operation to each side in order to obtain the solution. The next example, we could interpret this a couple different ways. We could say that this is a negative 1/7 times a w, and that equals 6. Well, what is the multiplicative inverse of negative 1/7? Well, it is a negative 7 over 1. So, if I multiply this side by the multiplicative inverse negative 7, then I need to take the right hand side and do the same. The two numbers multiplied give me a 1 in front of the W. And now that I calculate the right hand side, I get a negative 42. 1W is equivalent to a W by itself on the left, and so my solution is negative 42. If you look at the right hand side, you may say to yourself, well, what happened? How did I calculate negative 42? Well, I simply multiplied the 6 on the right by a negative 7. And so that sort of leads me to my different version of what takes place with this equation in order to solve it. We could have interpreted this equation as a W divided by a negative 7. Well, the opposite of division is multiplication. So, what's happening to my variable W? Well, I'm dividing it by negative 7, so to get the W by itself, I would multiply by negative 7. And what I do to one side, I have to do to the other. So I multiply the 6 on the right by negative 7. The negative 7's cancel, leaving a W by itself on the left. And 6 times negative 7 is once again negative 42. If you wanted to check your solution, take the original equation, which has a negative already, a 7 on the bottom, a 6 on the right side of the equation, replace only the W with a negative 42. We apply the double negative rule, which makes this a plus 42 over 7. And 42 divided by 7 is a positive 6. So that confirms our solution of negative 42. Example 9, here we have our P is multiplied by negative 2/3. Alright, again, a couple different ways we could look at this. We could say negative 2/3 is multiplying P, and the opposite of multiplying is dividing. And so I could write my fraction bars on the left and right side of the equation. So a negative 2/3 divided by a negative 2/3 would simply give me a 1, and then I have my P to the right. So on the right side I have 1P, the negative 2/3 sort of canceled. And now on the left side I could write negative 15 divided by negative 2 over 3. When you are dividing and that involves fractions, then you keep the first fraction the same. You switch to multiplication, taking the reciprocal of the second number or fraction in this case. On the right, 1P is the same as a P by itself. And now on the left, if I multiply 15 by negative 3, I get a negative 45. And then if I multiply the 2 by the denominator of the 15, I get a 2. And so our answer P is a negative 42 divided by 2. We could rewrite this as a decimal number, 22.5. But in my opinion, either one of these answers, the fraction or the decimal version, would be acceptable. Okay. I will show you an alternate version of solving the same one-step equation. And that would be to say that in order to get the p on the right by itself, we would simply need to multiply by the negative, or I'm sorry, the multiplicative inverse of the negative 2/3, which would be negative 3/2. We simply flip the fraction upside down and keep the same sign. So if I multiply the right side by negative 3/2, I go to the left and do the same. A number times its multiplicative inverse results in a 1. And so again, on the right, I have a 1p, which is the equivalent of a single p. And I end up multiplying 15 by negative 3/2 again, and that is going to give me the same number, negative 45/2. Alright. Example 9b. I will solve this only using one method. I will use the multiplicative inverse method. And so I look at this as a 3/7 times u. I want to get rid of the 3/7, so I multiply by the multiplicative inverse, 7/3. That will cause me to get a 1 in front of my u on the left. And now on the right, I could rewrite this as a 7 times a 12/3, which is the same as 7 times 4, getting a 28. And I could also remove the 1 in front of the u. In the end, u equals 28 is the solution. And again, you could take 28 and plug it into the original equation, and you'd get 12 once you calculated the left-hand side. But I'll leave that to you. And now our last page of chapter 12. Here we have a decimal number. What we can do to solve this equation, and again it's just simply a one-step equation, we could say out loud that W is divided by 2. Well, what's the opposite of dividing by 2? That would be multiply by 2. So to write that out, I would place W divided by 2, or W over 2 in parentheses, with a 2 on the outside. And to show that I am carrying out the same operation on both sides, I put the left-hand side 12.8 in parentheses with a 2 on the outside of it. The 2's on the right cancel, leaving the W by itself. And now I carry out the multiplication on the left side. 2 times 12 is a 24. 2 times a 0.8 is a 1.6. If I add the two together, I get 25.6. And there's my solution. W equals 25.6. And example 11, the last example of the chapter. We have W with a minus and a 5 on the bottom equals a negative 51. I will rewrite this as a W divided by -5. And so I want to undo what's happening to the W. And that would mean that I need to multiply by -5. So I put both sides in parentheses, and then on each side I put a -5 outside the parentheses. On the left, the -5's cancel. I'm left with a W, which is the goal of solving an equation, variable by itself on one side. And then I multiply 5 times 51, and I get 255. And the double negative rule says that the 255 would be positive. And I have now solved this last equation, W equals 255. Again, you could always plug the number back into the original equation. This minus is the result of the equation, 5 on the bottom, and now I plug in a positive 255. I didn't write the plus sign. And does that equal -51? 25 divided by 5 is 5. Bring down the 5, divide it by 5, and you get a 1. So yeah, okay, this equals the right hand side, and so our solution checks out. And that completes chapter 12.